I'm Alan Warburton. I'm an artist working with computer graphics, and this is a film about my exhibition at RGBFAQ Gallery in East London, which opened in late 2020 and runs until March 2021. It's been a difficult year to put on an exhibition, so this film is really just a way of sharing the project amidst ongoing travel restrictions and lockdowns that have put such a strain on the arts recently. And for background, and for those who've never heard of me, as an artist, I work mostly with 3D animation and design software. I make images, films, installations and sculptures, and a lot of my work tries to understand the cultural impacts of software and digital image technologies. The themes of my work come across most directly in the video essays that I've made, where I've talked about the unstable value of digital images and the labour involved in producing them, the history of CGI and its weird frontiers, or the cultural algorithms that have fed surveillance technologies. This exhibition came about in 2019 when RGBFAQ asked me to contribute to their 2020 programme, which is on the theme of systems. And I wanted to use the opportunity to try and dig a bit deeper into image tech and to sense the forces shaping the past, present and future of computer graphics. And I've worked with CGI now for almost 15 years, and I feel it's been the golden age in many ways. As consumers or producers of images, we're all now part of this massive image factory that pumps out content at higher resolutions for more platforms and devices, with more spectacular effects, more accurate simulations, or more responsive interactions. And the drive of progress is so huge and widespread that really the elephant in the room is the idea of progress itself. What is this addiction that computer graphics feeds? Why is it such a money spinner? Why will people pay so much for a game, or a phone, or a console, or a film, simply because it demonstrates an incremental improvement in graphics? So I wanted to look a bit deeper and to answer this question somehow, to zoom out and try and get a sense of what games and visual effects and virtual reality have in common, what underpins them and what drives them forward. Sometimes I use the phrase future art histories to describe this approach to digital images because I'm really interested in the broad strokes of this technology as applied to art. And I'm also interested in the kind of concept of technology in itself. And if I've come to any conclusions, it's that at the most basic level, it's the job of technology to sort of recursively reduce the gap between the virtual and the real, between theory and practice, or the simulation and the event. It exists to predict and control outcomes. Which is why it was so ironic that I happened to put on this incredibly ambitious exhibition in 2020, the year that most expected outcomes just didn't happen, and the year that predictive simulation repeatedly faced up against the real world of politics and capitalism. So 2020 was all about simulation versus reality, and it's fitting then that this exhibition actually started in virtual space. Right at the start of the project, I built a replica of the gallery in software to help me plan out where works would go and what the viewer experience would be like. And this was really just a way to sketch out ideas at first, but then of course the virtual world began shaping the show, and the white cube started becoming a black box, inheriting some of the logic of software. I used these big geometric shapes as placeholders for work to begin with, and then they started to become the works themselves, or at least screens that I could project onto. The centre of the real gallery overlapped with the centre of the virtual space, which is called the origin, and it's marked by this little gizmo that looks like this. It's a three-pronged object that's present in many types of software, whether it's animation, architecture, games or engineering software. And this origin axis became my motif for the show. It's like an anchor or a compass for virtual space, where red, green and blue indicate X, Y and Z respectively. And as I try and show in the essay, this colour-coded compass helps us understand more about how images work in simulation tech like 3D software, AR, VR and games, etc. The origin axis really is simulation encapsulated. So in a moment you'll see the exhibition, or a simulation of it, and I won't spoil the argument, but one of the interesting things about the process of designing an exhibition virtually is that while it's supposed to reduce the chances of things going wrong, simulation itself can introduce problems. The complex translations between the virtual and the real, using various software packages to calculate scales and distances and optics and perspective, is something that a lot of artists and designers struggle with. And for a couple of months I was working 110-hour weeks to mitigate problems as well as trying to animate everything. I had spreadsheets and briefs and plan A's and plan B's and plan C's, But what I hadn't really anticipated is that, like the exponential growth of a virus, errors imported from the real world propagate into the virtual, and they only grow when you return them again into the real. I always think of the Ariane 5 in relation to this. It was this rocket that in 1996 it exploded a few seconds after liftoff, and the reason it exploded was that the simulation for the launch had a glitch known as a floating point error, which might be familiar to gamers or people working with computer graphics. And this happens when a virtual object moves too far from the origin, and the coordinate system freaks out about decimal points, and you'll get positioning glitches and error messages, or the object might simply disappear. And that's what happened to Ariane 5. And it kind of goes to show that software problems can infect the real world in catastrophic and really unpredictable ways. So here's my kind of inconclusive and sketchy spatial video essay about colour, space and simulation, which started in the real world and then jumped to virtual 3D, and then was rendered as 2D, projected back as 3D, and now reaches you as a 2D film. In the mid-20th century, the age of computing began. The early computers developed for World War II led to the Cold War arms race, to nuclear research, satellites and space travel. What started as methods to calculate the trajectories of neutrons, shells, rockets and missiles soon found applications in weather prediction, fluid mechanics, atomic energy research, thermal ignition, cosmic ray studies and wind tunnel design. The computers of this time were all geared towards high-stakes simulation, the avoidance or creation of catastrophe. Simulation allowed trajectories to be plotted, planned or avoided, patterns to be sorted from noise, enemy forces to be mapped or intercepted, and weapons and vehicles could be designed to protect or destroy more efficiently. And out of this explosion of activity came computer vision and computer graphics, ways to see the world and ways to simulate it. This is the dual apparatus of the computational image. The trajectories of the computational image have been tracked by many cultural theorists over the past 30 years. They've talked about hyperrealism, images as weapons, and the effects of software on culture. More recently, in the fields of new media and post-photography, efforts have been made to understand the various subspecies of computational images, all characterized by their hybrid status as both image and data. And while a lot of current thought is focused on computer vision, that is, how computers see the world, this exhibition is about computer graphics, which harnessed the technologies of war and used them to simulate new, immersive worlds. And in doing so, CGI exploded the image, fragmenting it into colourful, data-rich elements that have since infiltrated all kinds of imaging technology. This is the story of a new mode of vision, an exploded image. How it came to be, what it can do, and where it might be pointing. The virtual world began inside a black box. Early military supercomputers, like the ENIAC, were programmed to simulate the trajectories and effects of neutrons, ballistics and missiles. Their 3D calculations manifested as illuminated bulbs, readouts or drawings. Interactive visual interfaces, like the one used by the SAGE air defense system, were slower to develop. Then, in 1963 at Bell Labs, mathematician Edward Zajac, frustrated with having to puzzle over pages and pages of computed numbers, programmed a visual simulation of a communications satellite in orbit. With spatial coordinates fed into the computer via punch cards and printed onto microfilm, this was the first small step towards a new world
of illusionistic digital space. Zajak's wireframes were an attempt to solve a problem endemic to computation: how to intuitively represent massive amounts of spatial data. And he wasn't alone. Other researchers also realized the need for a 3D visual interface, and there was general agreement that a standard protocol was essential, one that could go beyond simple object skeletons to display complex shapes with colored surfaces that cast shadows that reflected and refracted light onto other objects. This was easier said than done. In theory, the path tracing algorithms already used by ENIAC to compute neutron trajectories could also be used to describe precisely how photons illuminated objects in a virtual world. But it would involve tracing billions of light rays every second. This was an impossible problem, bound on every side by computational limits. What's more, it wasn't just a matter of computing one image. Programmers had to define an entire system of vision, one that could simulate all possible viewpoints and any visual phenomena. They had to program the laws of vision for a simulated universe, but their hardware could barely depict something as simple as a cube in front of a sphere. These limits meant that computer graphics were realized slowly, piece by piece, often using clever economical hacks and workarounds. These include shaders that faked the interaction of light on a surface. A lot of shaders bear the name of their inventors, like explorers or astronomers. These are the people who mapped the contours and constellations of the virtual universe. Image buffers and culling processes that decided what geometry was visible at any one time and removed anything not in view from computer memory. Image textures that give the illusion of complexity to low-resolution shapes. Instead of 3D modeling intricate details, simple objects are just wrapped with 2D images. All these techniques demonstrate the ways that early 3D simulation worked around computational limits. These graphical shortcuts were inherited and are still evident in open-world games where everything is optimized for speed. Objects are just intersecting shells. Light and shadow don't always work as they should, and details are faked with image textures. Mirrors especially show us the limits of virtual worlds. They're often broken, fogged up, or conspicuously absent, and that's because every reflection doubles the calculation in a scene. Likewise, when you reach the edge of a game world, things often grind to a halt, and this is because the coordinate system of 3D space is governed by decimal points. And when centimeters turn to miles, things get tricky. You'd think, given that computing power is always in flux and that the eye of the needle is always getting wider, that we'd be able to fit bigger camels through it. But a modular protocol, defined by economy, had already been constructed, and it was useful for packing more spectacle into computer graphics. Even in the late 80s and early 90s, when ray tracing began to be feasible, these hacks still prevailed. And so the logic of the black box, as a whole of broken mirrors, a collection of clever cheats and hacks, had been defined. And it became the foundation on which other, bigger problems would be solved. Visual effects is one of those bigger problems. Digital VFX only really came into its own in the 1990s, and it marked a big step up from the graphics you'd see in games or in computer interfaces. Detailed, often photorealistic scenes were created slowly by many artists and even more computers. Fitting these kinds of images through the eye of the computational needle was a lot more challenging. The most important feature of VFX is that it integrates real, two-dimensional filmed footage with virtual 3D renders. And this requires another set of technologies, built around the clever hacks of the 60s, 70s and 80s. These include camera arrays that captured scenes from many angles, camera tracking or match moving that analyzed footage and extrapolated motion data, creating a virtual camera that moved like the real camera, motion capture that used tracking markers to record the skeletal movement of bodies, and then reapply this to virtual characters. Green and blue screens that allowed actors and objects to be separated from backgrounds and inserted into virtual sets. And light probes that captured on-set lighting conditions and reapplied that illumination to rendered virtual objects. These are just some of the ways that VFX bridged the gap between 2D and 3D, using rich sensor data and computer vision algorithms to convert images into spatial data. And as we've seen, computer graphics does the opposite, converting spatial data into images. But the big issue for CG is that it was hard to preserve all that rich data from virtual space after an image had been rendered. Think about it. An artist slaves over a shot for months, then waits weeks for it to render, only to find out there's a fatal mistake. The lighting is off, or the motion blur looks wrong maybe. All that 3D data is now flat 2D pixels. Re-rendering takes weeks that the artist doesn't have, and unflattening the image is impossible. But there is a solution. And out of all the innovations in computer graphics, this might be the one that has the most wide-ranging consequences today. It turns out that the best way of preserving 3D data in a 2D format was to output not one, but many images, each representing a different layer of information from the 3D scene. These fragments of the image could then be manipulated and recombined in compositing software like After Effects, Nuke or Photoshop. It's a bit like splitting light into wavelengths, or particles into subatomic elements. And in fact, the images are commonly called render elements. They're also known as image buffers, or G buffers. In games, they're sometimes called screen space shaders. Render elements are more than just collage Photoshop layers. They use 2D pixels to represent 3D information. And remember, in XYZ space, everything is known. That means all shape, motion, and position data can be represented using color, hue, saturation, and luminance. And this proves to be very useful. Common render elements can be broken into 4 categories. Beauty elements split the image into its key light-based components. Surface color, bounced light, refraction, glossiness, and more. Combining these together produces something like a final image. Matte elements are like masks, allowing each object or sub-object to be isolated and manipulated independently of the others. A different color is assigned to every object in the scene to aid that identification. Geometry elements use color to encode information about scene depth, object motion, and surface orientation. Here, red, green, and blue correspond with where in XYZ a surface is pointing. Here, color intensity shows the speed and direction of moving objects. And here, black and white is used to show which objects are close and which objects are far away. Utility elements are the deepest, most abstract level. They provide analytics for the computational process. This image shows where the render struggles most to compute light. Combining these images in a compositing package provides an amazing amount of editability over the cumbersome CGI image. It allows artists to interpret, intervene, reconstitute and resynthesize the image without having to repeat slow and expensive renders. A good way to think about it is as a kind of hyperimage, an image with bookmarks and switches embedded into it. And this hyperimage is how computer graphics manage to preserve the spatial information in a render, encoding 3D data in a 2D format. Together with computer vision, which, as we've seen, found many ways to extract 3D data from 2D images, these solutions produce a comprehensive image protocol, one that translates between real and virtual, 2D pixels and 3D space, bridging machine vision and human vision, data and aesthetics, It's a taxonomy of things that we can know from an image, as well as a toolbox of operations that can be performed on an image. But you might think, so what? It's all virtual. Well, that's where you'd be wrong. Computer graphics cause the image to explode, but in the wreckage of these render elements lay the seeds of something unexpected. Recently, there's been a tectonic shift in computation, and it's all down to advances in GPU architecture. GPUs fit many camels through many needles. They process huge amounts of data. They can compute billions of light paths a second, so computer graphics can finally attain the holy grail of real-time ray tracing, making images indistinguishable from photographs. And CGI's estranged twin, computer vision, is equally affected, because it can now take advantage of machine learning. Huge visual datasets can be analysed quickly using GPUs, which in turn help generate new powerful statistical models for interpreting and classifying images. But its biggest hurdle is getting hold of those datasets. It doesn't just need images, it needs hundreds of thousands of information-rich, segmented, clean, labelled images. Photographs don't come with all that data, but CG images do. And that's why computer scientists increasingly turn to synthetic datasets. Here's an example. In 2018, an animation studio in Canada made a synthetic dataset to help train an autonomous bathroom cleaning robot. They did this because the data they needed, photos of people's bathrooms, is hard to come by, unlike photos of cats and celebrity faces. 3D modelers created 86,000 computer-generated images of bathrooms by automating the randomization of fixtures, layout, and camera angles. Their dataset was produced at a fraction of the cost of photographing 86,000 real bathrooms. It also avoided the dirty ethics of data security and the bias of human-processed datasets. Synthetic data is big news. But there is an added bonus, and this is where the twist in the tale starts. As we've seen, CGI explodes the image into multiple render elements, each containing distinct operational information about a scene. This spatial data is incredibly useful for devices that need to interpret, navigate, and interact with the world. This is nutritious food for machine learning. Driverless cars are trained on render elements from driving simulators. Gaze detection algorithms are trained using synthetic eyeballs. AI-assisted medical imaging is trained on fake MRI scans. And aircraft detection algorithms are being developed using computer-generated satellite images. But as strange as it is to know that machines are learning about the real world from simulated images, it's important to remember the other side of the equation. And that is, a machine learning model, fed with render elements, looks at new images of the world and can infer render elements from what it sees. The photographic image, as we traditionally think of it, is simply a cryptic gateway to 100 other images and data points. And so, the exploded image keeps exploding, this time in your hands. iPhones analyze and segment your image, creating depth maps and filling in missing data using machine learning. Instagram AR filters use estimated normal maps to predict the contours of your face and map new features to it. Every app uses your phone camera differently, processing and capturing your images with different algorithms, augmenting them with machine learning models fed by different synthetic render elements. What this means for the image is important. In a way, there is no one camera, there is no one image. Both have exploded. Even a simple selfie is not one but many images. At the moment it's born, it's already manifold. Cut, reconstituted, segmented, filtered, indexed and sorted. It's born slippy. This kind of image carves up the world into probabilities and predictions. It's more informed by statistical operations than by art, photography, or cinema. It's a kaleidoscope of data, informed by other images, real and synthetic, and grounded not in truth, but in the inherited logic of simulation technology. And it's this technology that started with World War II simulations and evolved through hacks and patches in the subsequent decades, and that's now been embedded in GPUs, server farms, and smartphones, that has begun to define the possibilities for future images. It may even come to redefine past images, reaching beyond us, behind us, and between us, making connections we could never anticipate, providing insights into our histories, bodies, and behaviours that we have no access to or understanding of. So here's where the trajectory terminates and the simulated missile finally lands. Decades after writers warned of the triumph of simulation over real life, there's little doubt that we've gone through the looking glass and been turned inside out by computation into a new post-photographic world of synthetic images. But if the story started with the creation of another world inside a black box, a world that grew and grew as it was fed more and more, then it must end with a question, and that is, are we still outside the box?